Okay, we are back. So let's talk about electrical. So in electrical, let me go down here and kind of show you what an electrical plan looks like. I've got one open. I don't have one open. Let me open one right quick. Okay, so here is an electrical plan. And obviously you can see that we have some ceiling fans that's going on. These little things here are recessed lights. We have plugs. So if it has two lines on it, it is a plug that has two plugs in it. If it has a single line on it like this, then it only has one. You don't see these very often. If it has lines on it, let me explode this. If it looks like this, come on. If it looks like this, then it is a 4-gang box, meaning that it has 4 plugs in it. We have switches, we have 3-way switches, and we have 4-way switches. I don't see a 4-way switch on here. Let me go upstairs. There might be a 4-way switch up here. Nope. No 4-way switches up there. I'll explain to you what a 3-way and a 4-way is. Of course, we have some phone outlets. These are phone jacks. This is a light fan combination in the bathroom. We have GFI, ground fault interrupters, and I'll explain what that is as well. And then we have, this is a 220 volt. So this goes to the dryer, and then there's generally one for the range. So we've got a 220 volt range outlet there as well. I kind of wish that we would come up with something that would tell us how many plugs they have. So a dryer can have either a 3-wire plug, or they can have a 4-wire plug, and I'll explain it that. But there's really no symbol to distinguish the two of them. So that can be a little bit of a headache to some people. So we have regular screw-in type lights. This could be just a drop-down hanging type light. And well, let me go down here to the electrical symbol, and you can see them all. So I've got the wall switch, the 3-way. I don't show a 4-way on here because it didn't have one. The 220 volt outlet, and this should not say duplex outlet because it's not a duplex. Duplex means 2. So it's actually just a 120 volt receptacle outlet. It's not a duplex. We have the ground fault interrupter. We have a floor outlet. So was there a floor outlet? Yes, there was. So here's a floor outlet, and there's a floor outlet. So they go directly in the floor. Floor outlets can be a little bit of a problem. If you're sitting around watching the football game, you got your beer, you got your popcorn, and somebody makes a touchdown and everybody goes nuts, and you turn that beer over and it lands on that floor outlet, then it's going to light your world up. So the overhead mounted fixture, again, is that screw-in type. And then this, which is illegal now in the code, is a pull switch. You can't have a pull switch outlet, or excuse me, a light anymore. That's gone the way of the dodo bird as well. And then you've got the light mounted to a wall. So this could be a wall sconce on that one. You've got interior spotlights, smoke alarms, the ceiling fan. We throw a hose bib on this because we don't really do a plumbing plan in any other place. And then we have the 2-foot LED light strips, 4-foot LED light strips. We don't even use a fluorescent light anymore, like the two bulb fluorescent lights. Don't those have gone as well. They've gone bye-bye. Garbage disposals, phone jacks, television receptacles. So this is a coax cable. So in a bedroom, you're going to have a coax cable in here so that we can plug up the TV. Again, this is something we still put these in all of our houses that we build, but a lot of the times, most TVs nowadays are smart TVs and use Wi-Fi signal rather than a cable. Some of these houses are built out in the middle of BFE, and this is, they don't have very good Wi-Fi signals. They don't even have coax cables in them. Sometimes they still have the regular telephone plug-in that uses a dial-up in some cases. So it can be a little tricky sometimes depending on where it is. A vanity light strip is that energy sucking device that goes over a mirror that you put 111,000 light bulbs in it so that mama can see how to put her makeup on. Track lighting, which is a type of lights that can be focused and pointed in different directions across a long track. And then we have the exterior floodlights. A lot of these nowadays are motion sensor type external floodlights, and you'll see them in the corners of houses on a mounted to a soffit or something. So that is, in a nutshell, pretty much a electrical plan for a house. So let's talk about what goes on in there. Obviously, we're going to have a power panel. So let's back up here just for a minute and let's look at our house. I'm going to hide that again. So let's say that we have the power company here, and I'm going to draw this god awful looking thing that's up there off of Interstate 26 there that you can see. And this is, and that was, I think it just switched over to natural gas if I'm not, if I remember correctly. It used to be a coal burning, so we burned coal in here for years and years and years and years, and it turned a generator, or excuse me, it heated water in here, and we got the water boiling, and it went into a generator that made it go roundy, and in the process, we ended up with electrodes moving across a power line at about 13,000 volts. So it's going out. So we also have a ground line that comes out and goes directly into the ground. So you're going to generally see one line coming out of this, a big massive line coming out of it, and then you're going to have this ground that goes in to the ground. And that's why we call it ground. So as it goes in, getting closer to your house, it goes into a transformer, and you'll see those transformers up on poles. And these transformers transform this power from 13,000 volts down to two, not just one, but two 120 volt lines. And from this as well, you will have what is called a neutral, but it's a ground. This runs, excuse me, let's change colors here. This runs into the ground, hit the pole. It runs to your house, to the power panel that is outside the, not the power panel, but the meter base that runs outside. And then this runs inside to a great big box, generally in the house, that has 120 volts going along. How can I draw this? It looks like this. There's I messed up. Let me just show you a picture right quick. So electrical, actually, let me just show you electrical meter base. So the electrical meter base is put on the house. This is the, this portion of it is the homeowner's responsibility, the contractor's responsibility. And so you can see that there's a couple of lugs here, and you can put them here or here. So the lugs go on here. This is 120 here, 120 here, or vice versa. So you're going to have power coming in. It generally comes in from, if it comes in from the top, it's going to leave from the bottom. If it comes in from the bottom, generally it leaves from the top. They can both come off of the bottom, but then you have to work it around there. So let me explain to you what I'm talking about here. So the power is going to come in from the pole, and you're going to have 120 volt locked to this lug, and you're going to have 120 volt locked to this lug. That grounding wire that I was telling you about goes into the grounding lug here, which I should have changed colors. Where's my colors? Green. Comes in and hits into that lug. Now this is going to also come off of the bottom of this. It's going to go outside the box, and it's going to go to ground. All right. You have to put 2 grounding rods into the ground here, and these are tied to both of those. From there, then off of the bottom of this lug here, it's going to go down and into the house. So we've got 120 volts each side that's going to go down and into the home. This is from the pole. All right, so how does this work? So what happens is the power company comes and they put this little glass meter on there. As a matter of fact, got one right here. So this is a meter. So you might have to click on my picture to make it come up, but this is a meter, and it was given, this is an old meter. My wife works for the city of Morganton, and I use these in my classes to kind of show. And when I say that it's an old meter, see how it has the little dial on there? And so when you use like the dryer or the stove, this thing turns at a high rate of speed through here. And then these little indicators will go round, and they know how many kilowatts per hour you use. So nowadays, these are all digital. And so this is, the way of the dodo bird. So one of the engineers over at the city of Morgan gave me this so that I could show you guys, but it has these 4 prongs on the back of it. And so what it does is, so the power coming from the pole goes into these 2 top ones, and then off of the bottom ones, and then the power that is going through this is red. So this is a watt meter. You can buy simple watt meters, and so this is the watt meter that reads kilowatts. And so this is a digital one here. You can see how the little plate on the front of it is digital, where the one that I showed you is kind of similar to this. This has articulating numbers on it, where the one that I had just had just little rotator knobs on it. So this is how that thing is wired up, less the ground. Obviously, they haven't put a ground in this one here. Here's one with the ground. It works a little differently. No, that's not right. There we go. Is there a bigger picture? Maybe not. So how about that one? Not much better. That one's a little bigger. Okay, so you can see it coming from the pole. You see it going into the house, and that's how that works. So the grounding rod, you can get those steel or you can get those copper, and they look just like this. lost it all of a sudden. You can see it sticking out of the ground there, and then the ground wire is attached to it with the grounding rod clamp. So this is old school. Nowadays, you've got to have at least 2, and some places you've got to have 3. So these are not the easiest things in the world to put in the ground. They're 8 foot long, and you know, when you're trying to bang on a 8 foot long, 3/4 inch piece of copper, it will bounce in the middle of it. So there's been 100 different ways that you can try to get this in. I used to put them on a drill. I had a huge heavy duty drill, and I would clamp this sucker in there and drive them in that way, turn on the drill, and it just screw into the ground. There is a pounder. Let's see, grounding rod driver. It's a little tool that looks like this, and it beats the hell out of trying to put it in with a hammer like this. So this is a hollow tube, and it just goes over top of this. So this is hollow up through here, and it keeps you from pounding off of it. You can buy these little things here that go onto a rotary hammer, and you can use those to drive it in. But they're not. This is what I was always doing. I just putting that heavy duty drill in there and just driving it down in there. It's not an easy thing to do. If it hits a rock, you're screwed. You might have to pull it out and start again. So here is the view that I was trying to say. This is what is required in the house now. So not less than 6 foot apart, 8 foot deep. Generally, you want to dig out and get this completely, totally under the ground. This would not be a fun thing to hit with your lawnmower or anything. There are other ways that you can do it. Some of them are not always looked at as very promising to some building inspectors, especially the horizontal one here. They don't like that. 45-degree angle is okay. They like that. They will accept that, but they really like for it to be, 8 foot deep in that manner so that it protects you 100%. This, when I say protects you 100%, that's what it's meant. It is meant so when you touch something and you get shocked, you are acting as the ground. And so the more ground you have, the least resistance is where this is going to run. And so that's where it will run for sure. Let me go back up, kind of explain to you what electricity is. So we have what is called AC electricity. AC electric. And we have DC electric. And so I know it's confusing, but let's start with DC. DC, and here I'm gonna put this into the best way that I know. That's not what I wanted. Dominoes. Okay, so let's go to videos for a second here. So you know how dominoes work. And so basically what happens is the flow of the dominoes runs in one direction, and then you see how it kind of works. One hits another, hits another, hits another. All right, so with that thought in mind, let's think about how this electricity works in a car. So DC is in a car. So we've got an electrode here. And electrodes are like T90. They're so small, we have to have a electron microscope to see them. They're so small, okay? So when we think about the movement of electricity, we think of, you know, this electron moving from one point to another point, but that's not what happens. What happens is it in DC, so DC electricity, basically it's that domino effect. So this one hits that one, which moves that one, which moves this one, so forth and so forth and so forth and so forth and so forth. And they move down the wire until they, you know, in DC, we have a battery. And it runs down the wire until we have a fan or whatever that we've got going on there. And this thing turns on, goes roundy roundy. Okay. This electron right here did not travel the entire way to get to here. All it did was it just bounced over from electron to electron to electron to electron to electron until you get down to this point here, and then we utilize the power. So that's in a nutshell how DC works. So let's think about AC. So when we're thinking about AC, the best thing that I can tell you here is Newton's Cradle. So you guys have played with this as children, I know, and you still play with it sometimes. If you had one, you'd play with it now. A Newton's Cradle is how the electrons move in alternating current. So AC, it works in both directions. Pretend like these balls are electrons, and if you move one electron, you're going to move one electron at the end of the line. If you move two electrons, obviously you're going to move two electrons at the end of the line. So the stronger your current is, the stronger your result will be at the end. And that is how alternating current works. So when we're thinking about alternating current, again, it's the same thing. We've got our generator here, and it's sending out these electrons, or actually it's poking the electrons, and they work in one direction until they reach their source. And then they turn right around and they come back. All right. So it's not a whole lot of going up and down. It's a matter of going boink, boink. I know that sounded stupid, but you know, we're moving this, it moves back. We move this one, and when we move this one moves forward and move back. This all happens absolutely so fast. How fast? The speed of light. That's how fast this is moving. So you can imagine, let's say for instance, I got a bowling ball. Okay, so we're at the lane here. We're bowling. We got our pins set up down here, and we're getting ready to throw our bowling ball down through here. Except there's another bowling ball here, and another bowling ball there, and another bowling ball here, and another bowling ball here. So we throw our bowling ball and hit this bowling ball. This bowling ball hits this bowling ball, and so forth and so forth. By the time it gets to here, this bowling ball is going to be really, really, really weak. So that's what happens with AC as well. In DC, we can go hundreds of miles and still have strength in the DC. But AC works like that bowling ball, and this hits this one hits this one, this one hits this one. Eventually, we have something that's called line loss. And line loss is when, you know, we have something very strong and big and happy over here, and then by the time we get to the end here, then he's a little, you know, he's a little bitty moron that can't pull a greasy string out of a cat's ass type thing, you know. So this line loss kills us when we have a long distance to go in AC. Okay, so in the house, we have a ton of different things that have to be wired up very much differently. And let's talk about the power panel. So this is what is generally on the inside of your house. This goes on the outside of your house. This will be on the inside of the house. So let's see a good one anyway. Is that one a pretty one? It's not too terribly bad. Let's take a look at that one a little bit better. So you, no, can't use that one. That one's a sub panel. There we go. Again, it's small. What was that? That one's bigger. Okay, good. Okay, so sub panel, remember that. I'll come back to that in a minute. Here is the panel. So you have a main breaker on here. Notice that it says 200 amp. 200 amp. In most houses, that's what you have coming in is a 200 amp. So this is a breaker. Let me back up and show you something else. So this is something that's kind of old, which is a fuse. Perfect picture. These were screw-in fuses. And so they pretty much like your fuse to your car, they had a little piece of wire in here, and you kind of see it in that picture there, just like the old type of fuses. And if something were to use more power than this little fuse, this little piece of thin wire in here could stand, this would burn in half and you've blown a fuse. I'm sure you've heard that expression, you've blown a fuse. A lot of times today it talks about people who get mad and have a temper, they've blown their fuse, but this is what, they've basically had too much power and it has burnt that little wire in two. These could be dangerous because when that burns, it creates an arc, and that's why these were always encased in glass. So people, you had to have fuses on hand, otherwise and you got to remember when these were in effect, on holidays everything shut down, on Sundays everything shut down, at 9 o'clock everything shut down. I mean, hardware stores closed at 5, not 5:30. And if you blew a fuse, you were just SOL. You couldn't get a replacement really quickly. So people would take these off. They would put a penny in it and put this back on. So what happens when you push that penny into this socket? You can imagine. Go stick your finger in a light socket and tell me what happens. People were getting killed. So let's talk about electricity a little bit more here. So we have amps, and we have watts, and we have voltage. Well, let's put that into water. Matter of fact, I remember seeing something that wasn't not too far ago. Electricity as water. Understanding basics. And I may have this on there, I don't know. So here we go. Voltage, current, which is amps, and we have resistance, which is ohms. So voltage is your pressure, current is your volume, and then resistance is that line length stuff that I was telling you about. So in water, if we had a water pump on, we get pressure. The diameter is going to give us volume, which is the current. And then if we got sand in there, then that's a longer line. Okay, so that is the understanding. And So watts is used power. So I over, is it V over I or I over V? Let's see for a second. Can't remember. Oh, right there it is. I over R is equal to V, but watts is also connected there somewhere, and I can't remember which one it was. Watts or kilowatts is the rate of the water. So we're actually collecting this water and seeing how much it is. So how fast can we fill up a bucket? That would be, kilowatt hours and so forth. It can be a little bit confusing sometimes. So most of the time we're dealing with 120 volts or 220. And how do you get that? Actually, let's change that for a second. Let's call, and I know I said it was 220, but I want to call it 240. So from the power company, they guarantee that 120 volts and 240 volts leave their factory. But when you get to your house, they can only guarantee 110 volts and 220 volts. So don't let these numbers mesh up. I know a lot of times I call it 120 and 220. It's just simplicity for me, I guess. But really, coming from the factory, it's 120 or 240, and it's 110 and 220. So how do I get 240? Well, you take two 120 volt lines, and that equals 240. At your house, you have two 110 lines, and that will guarantee you 220 volts at your house. Because the distance, because Sally's house might be 10 miles past Joe's house, then Sally may not get the full voltage. So Sally may only get the 110, 120, where Joe gets 120, 240. Okay, so that they leave themselves a little bit of room there. So in that, there's that stupid floating thing in my way again. We got old Joe here. Joe's he's been working all day, and he is working on electrical at home tonight. So amp is that current, it's the power. All right. So if he touches this line, he's going to feel a little shock only if he's grounded really good down here. And he's going to feel the shock here because this is positive and this is negative, and it runs through his body in such a way. Okay. And he feels it. Now, over on this other side over here, he's got a ground that is negative. And he touches this positive on this side, and it runs from arm to arm across this. And what's in the middle of his chest? His little bitty heart. 0.065 amps is what it takes to kill a person if it crosses your heart. All right. So you will see electricians, linesmen, they'll have these special gloves that actually has a chain between the two gloves so that it bypasses their heart. And if they ever touch anything, and these gloves are like super thick rubber too, you definitely couldn't pick up a coin on the ground with these gloves. It is there to protect that heart. It doesn't have to go from arm to arm. It could come from the right arm to the left leg, or the left arm to the right leg. If it passes over your heart at 0.065 amps. So how small is that? A circular saw generally uses 15 amps. That gives you a little idea of how little this is. If it goes across your heart, you're a done deal. Okay, we'll just go ahead and put his eyes down. He gone, shot, dead. Okay, so it's super important. If you ever have to get into a box to do anything, as I tell all of my students and my children especially, they all know this, you go into it one-handed. All right, so what I'm saying is, if you ever have to do anything in this box, number one, get you a plastic milk carton. You know what I'm talking about? Plastic milk carton. Not plastic milk carton, crate. So I'm trying to think of crate. All right, so a plastic milk crate. Turn that sucker upside down, put you a wooden board on it. Stand on it and go into these panels one-handed. You can touch anything you want in here as long as it doesn't pass through your heart and you've not got any ground. Okay, so if you go into it one-handed, you're not going to touch anything but what needs to be done. Because if you go into it with two hands and one hand, or even if you touch this and your wrist is touching that, it's going to light your world up. Okay, this box is grounded. See those little things right there? That's grounded. All right, if you touch the hot, you touch the cold, you're gone. It's going to hurt. All right, so one-handed. Now let's look at this one here, and I want to explain to you about this 120 240 thing. So in here, you can see the red wire here, or the red and black wire. That is 120 volts. I keep wanting to do degrees. And on the other side over here, we have 120 volts as well. Notice that they go into here and you've got this funky looking thing here. This one here is connected to the blue line and the red side is connected to the red side. So every other one here, this one, this one, this one, this one, this one, and this one is connected to the red side. But also this one, this one, this one, this one is connected to the red side because they pass over. See how they kind of pass over? So every other one, this one's red, this one's red, this one's red, this one's red, and then we have the blue one. This one is blue, this one is blue, this one is blue, this one is blue. So this is blue, this is blue. And you'll notice that some of these are singles and some of them are doubles. Let me erase all of these lines here for just a minute. Let's look at the singles and doubles. All right, so I have here a single switch, but here I have a double. So this double is, he's got the red side and he's got the blue side, which this running out here, he's got two lines running out here. This is, sorry, 240. All of these singles running across here are 120. But anytime you see a double coming out of there, that is 240. So why do we need 240? I'm sorry?
Can you change the color on that writing?
Which one, the blue or the red?
The blue. You can't even, I can't read it.
Can't see the blue, okay? How does this look? Does that show up? Does the yellow show up?
Yes, much better.
Okay.
Thank you.
All right, no problem. So, so let's change this one to this. We'll change this here to yeller. There we go. All right, so anything that's going to come off of there, one or the other, is going to be 240 And the singles coming off of there are going to be 120. Now, why do certain things need 240 and why do certain things need 120? So when we're thinking about a light bulb, for instance, and in the light bulb, we have positive and we have negative. And when those two cross, and I'm going to use an incandescent here, when those two cross, this filament burns. It gets really, really, really hot. But remember that this is 120 volt coming to the light bulb. Now let's look at the eye of our stove. So on the eye of our stove, we have 120 volts coming on one side, and we have 120 volts coming on the other side. When they meet in the middle, this is burning 240 volts of electricity. Now here, this was tiny, 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 the size of a hair, okay, a human hair. This is as thick as your little finger. So this is going to have a lot more resistance, and it's going to use a lot more power to do the same thing. Obviously, when we turn on the stove, it gets red. But when we turn on the light bulb, it gets super bright, okay? This is indicating the temperatures of these two. Where this may be a max, where the stove may be a max of, say, 500 degrees, it's using a ton of electricity. The light bulb, and we'll say that the light bulb is 100 watts. 100 watts. And this over here is, it's like 200 or 2,500 watts. All right, big difference, big difference. Still, we're using 2,500 watts and we're only achieving 500 degrees. The 100 watt here, this old light bulb here can be in excess of 2,000 degrees. That's why we don't touch this, because it gets hot where we don't touch this either. But this thing gets super, super hot because the filament is so small. To reach 500 degrees on the stove, we don't usually use 500 degrees, but that's the maximum setting on it. But the stove and the oven have the same settings on there. So if your oven reaches 500 degrees, your stove tops will reach 500 degrees. So when you're on high, that's 500 degrees. But look at how much more electricity. I mean, it's what, 250 or 2,500% more than the light bulb. But because these are so thick, this is the best that we could possibly do. Now, something to be said about electricity. Electricity is 100% efficient. All right. Now you're thinking, wait a minute. I know that when I turn on this 100 watt light bulb, it makes my power bill go up. You're right, it does. In an incandescent light bulb, 10% of the power usage comes out in light. 90% comes out in heat. So over here, pretty much works the same thing. We use this for heat, and we've used this for light for years and years and years. So even though we are burning up 100% of the electricity, we're only using 10% for what we're wanting to get out of it. Where over here, we're using 90% to produce heat. So electricity is 100% efficient, but we've been using it for the wrong reasons in our light bulbs. So when we're talking about if we've got a light bulb in here that's the CFL, all right, so it's just a little, the pigtail looking thing. Can't draw one. This heats up a gas, all right? So it let's see, the equivalent to that is 100 watt. I want to say it's 28 watts equals 100 watt light bulb. Remember that when we think about a 100 watt light bulb, we're not thinking about the 100 watts. We're thinking about the lumens, and lumens are the brightness. Okay, this is what we should be thinking when we buy a 65 watt light bulb or a 100 watt light bulb. It's the number of lumens that we're putting out. This is only how much power we're using to get that number of lumens. So even smaller, we're talking about the LED light bulb. And the LED light bulb, you know, we still buy them in the same screw top fashion because that's what we come up with to begin with on the incandescent light bulb. But this LED, to get 100 watts, I want to say it's like 18 watts. But 18 watts, 28 watts, 100 watts puts out the same lumens. And you can also think of that as candle power. How many candle powers are they? One candle power is just what it is. It's one candle. So one candle power is that bright. So you can imagine, I mean, flick your lighter and that's how bright it is. Okay, let's see, let me clear this. Any questions on any of this so far? Am I making sense?
Yes, thank you.
Okay, all right, so we're buying our power, and the wattage that passes over this meter is what we're being charged for. Goes into here and then out to our branches, into our lines in here. And if you'll notice, there are two bus bars on here. One bus bar, let me just go back to the little drawing thing here. One bus bar here is the ground line. This is the ground. This runs outside and to the ground. All right, runs back outside, back into this box, and somewhere it runs to ground. I don't see it coming out anywhere, but it does, I promise you. I'm sorry, I'm wrong. This is the ground line that runs back to the power company. So this is the neutral. Let's put that at white, okay? Can you see that okay?
Yes.
So the ground line, I'm sorry, is over
the ground.
What's that?
Use the bright green.
The bright green, he says. Okay, bright green, this one.
Ah, that one, it's easy.
Okay, all right. So this side over here runs out and down and into the ground. All right. Technically, this one does too. Both of these are ground. If you'll notice, some of the white wires go into this side, but also there's a copper one right there. Over here, we've got a bunch of copper ones. We don't have any white ones running in that I see, but we have coppers all over here. So this and this is actually tied to the box. So that makes the box ground. So this is tied to the box. This is tied to the box. This runs back out to the pole. Not sure that it probably does run back to the power company, but it's actually, you'll see a lot of these lines, and they're let me see if I can draw this a little bit better way. You've got different colors. You've got so you've got, and I'm saying different colors, but basically you've got three wires that you can see that are running from the transformer to your house. Well, this ground, all right, the white one that I'm talking about is actually aluminum. And well, they're all aluminum, but it's open. You can see the aluminumness of it. Well, that is this, it's used as this wire here, but it is also used to hold these other wires. This is the only wire that has tension to it. If you'll look on your pole, this is connected to the house, this is connected to the house, but the other ones, you know, they pop up and go into the top of it. There's no tension on these at all. The tension is only on that bare wire. And so let's think about aluminum there for just a minute. These larger lines that you see inside this box are all aluminum. So you've heard me talk about line loss, and line loss has a lot to do with the material that it runs through. So let's make a list here. The best of the best of the best of the best. This is the best conductor of electricity that we know. Now, could we run our power lines out of gold? Well, it also is the most expensive. All right, so obviously not. And it's very soft. All right, so we would definitely have a problem here if a tree fell on or something, it would break easily. So the next one down the line is copper. I'm sorry, not copper, aluminum. So we use aluminum for the big wires. But if we used aluminum inside the house, the problem here is, number one, okay, it's cheap. It's only $1 there. And it's not soft, it's not hard, but it flexes. So let's talk about that. So we had, back in the 70s, manufacturers were building mobile homes with aluminum wire in the house. So when you heat up aluminum, it swells, all right? It gets big, all right? And when aluminum gets cold, it gets small, it contracts. So there's a lot of movement here going on. And what happens is, if you'll see these wires, there's black, there's red, there's white, and all of these are plastic coatings on there. When they swelled, they would break this plastic coating, and over time, the coatings would just fall off. So we had a lot of houses burning down because that aluminum wire was flexing so much when it got hot that it was degrading all of the insulation off there, and we had to do away with it. So this is, we'll give it 2 stars for being conductive. Now we get on down the line, we have copper. Copper is less conductive than aluminum, but it is more expensive. We'll give it $3 signs there because it's pretty expensive compared to aluminum. But this was the Goldilocks wire, the Goldilocks material to use there. So we found out that copper was the best one to use, but then we found something else out. So we were using a great big old solid piece of wire. And remember when I told you that the electrodes flow around the wire? The electrodes don't flow inside. There is no movement of electrodes inside the wire at all. They all run across the surface. So, you know, we would have to make our wires bigger and bigger and bigger and bigger and bigger and bigger to get the electrodes or the amperage to flow across this wire. But something that we did find out, that if we used a stranded wire where we have lots of little wires in there, but we had the same diameter as our big wire, then we were utilizing a lot of this space in here and we didn't even know it. So a stranded wire, is that about the right size? That's about the same size right there. I'll stop there. So the stranded wire, there's a more surface on there, and we can put more electrons in this wire and move them down the line. So stranded has a much better amp flow than solid. So they still use a lot of solid, but a lot of times you will see solids being changed over to stranded a lot of times. Now, Remember that you see solids a lot of times in AC where you see stranded a lot in DC in cars and stuff, because you need more amperage in DC than you do AC. Okay, so when we're running it through the house, we obviously have to, you know, do different wiring stuff on here. And that's what I wanted to talk to you about, a single wire. So let's take this one, for instance, and we have just a single switch and a single light bulb. We have the black in, now this is, again, let me iterate, AC is in a house. DC is in a car. So we're talking about AC, alternating current. And in AC, black, red are positive, white and green are negative. Most of the kind. Okay. How in the world did I do that? Green or bare. Okay. So if it's copper color, these are all negative, and that's sometimes. Okay. And the reason I say that is in this particular case here, we have power coming through the black wire, and see this little black tape on here? I don't want this to sound racist, because it's not, but this has always been what I have been told: down with white, back with black. All right, so that means when we go down to a light switch, we take the power down the white wire and we bring it back through the black wire. So we got the white wire going down with power, and it goes into this switch, and this switch just looks something like this, where we have the black wire coming off of it, we got the white wire coming off of it, and this switches back and forth between the two to give us the power to go back up through here. So it's going to move this power up, and we're going to send it back up the black, and then it's going to go into the light bulb. It's already got the negative wire here. The negative wire is there. It's already taken into this light bulb. The only thing that we're doing is we're switching. We're like taking this cap off and pulling these two apart to turn the light back and off and on. And that's what happens here. We're pulling those wires apart at the switch. So whenever the power comes into the ceiling light or any other light, if it's a wall light, then this is the saying: down with white, back with black. Always put you a black strip on there and put you a black strip on there to keep that straight. So let's talk about if you've got just another light down the road here, then you're going to do this wire, but both of these are going to be switched off of this. Let's talk about a three-way, if I can see one. Bam. Three-ways can be a little bit more tricky, obviously. So let's take a look at this. Maybe I didn't. Hang on. Here. So let's take a look at what's going on in this switch. When we had the single switch, we had that wire coming off of here, and we got the wire coming off of there. So when it's in this position, it's off. When it's in this position, it's on. In the three-way, we have two wires coming off of there, and we've got the common wire coming into it. So we have two two possibilities here. And the same thing happens over here. We have one wire coming off here, one wire coming off here, and one wire coming off of here, and these two. So we've got the power coming down, and it goes through here, and it's going to go all the way to the other side and into this one, across through there, and then it's going to go to the light bulb. If I were to switch this, then the power ends there, and it goes over to this one who is not connected. So let's say, for instance, I come into this room and I turn the power on here. Bam. Whoops. Power's on. The power runs across the room, into this, across this, and through the light. So when I get over here, I'm going to turn the light off. And the power ends here. It doesn't go up through there. The power's running in on this one, across through here, and it stops. So Fred is going to come over here, and he's going to turn the light back on by moving this one over. And then it runs across through there and runs up to the light bulb. And then when he gets over to the other side of the room, then he can turn it off. And that is how the three-way light works. Now, if you don't get these wired up correctly, two things are going to happen. Either A, it ain't going to work, or B, it's going to blow up something because you've wired a positive and a negative together. So it takes a little, like I say, it takes a little bit of practice to do these three ways. Now, what about a four-way? Remember, I told you about a four-way. So let's see, four-way. Might just have to do me a search here. Four-way. Run out of time really quickly here. Okay, so here's a four-way switch, which means that it has two, or it has three, wait a minute, what? Open and new. Oh, I know what it is. Okay. So in this case, we have to have one switch in the center that has four switches. So before we had a three-way. Okay, so we had 3 points in here, and over on the other side, whoops, we had 3 points. And, you know, as long as these two were connected correctly, then the movement of this from back and forth would send power to the light. Well, now we've got this four-way in here, which looks like this, and it switches back and forth like this. So we have the power coming in, we got the power going to the light, and this is going to be hooked up here. This one's going to be hooked up here. This one is going to go to there. This one is going to go to there. So power is going to come in, it's going to cross down, go over to here, and it's going to go up to the light. But if I get rid of this one and I switch it differently, I don't know why this doesn't work half the time, and I switch it here, then power comes up, goes over, switches over, comes up to there and stops. So I can change this one over to this side. Power's going to come in, go over to here, but it's not going to go anywhere here. So now this one is going to have to be switched the other way so that it passes over and goes around. So that's kind of how a four-way switch. A four-way switch works with 2 three-ways and a four-way. And the only reason it's two-way, four-way is because of the number of points that are inside of the switch itself. Whew. Any questions?
Thank you for the explanations. Not so much. Why would you use a four-way switch anyway, though? Like, what's the point of adding that in there? It just seems like a nuisance.
Let's say that in this house here,
thank you,
Okay, so I have this house and I have a light in the great room. Okay, so I come in the door and I could have a light switch here to run these lights. But then I'm going to go out the mudroom and I can turn them off. But what if I come in from the back porch? I can put a switch here, here, here. Even if I had a back door on this over here, I could put another four-way here and I could turn it off, turn it on, or excuse me, turn it on, turn it off, turn it off. Damn it. Off, on, off, on. Off, on, off, on. I could go around there all day and I could turn either one of them on or off with either of the switches.
Okay.
Okay. So, you know, in most cases, like for instance, this room here, in this bedroom, we're going to have this light that's in this bedroom is going to have two, it's only going to have two switches. And it's going to have a switch here when you first come into the bedroom, and it's going to have a switch here at the bathroom so that if I get up in the middle of the night, then obviously I can turn it off here and it's going to, you know, I have two. So these would be two three-way switches. This one over here, we have one. We're just going to have a single, and we call it a single even though it's a two-pole switch in here. You got off and on, so there's two poles. Does that make sense?
For the most part, yeah.
Okay. So if I'm here, I should have drawn this for you to begin with, then I could put a switch here, I could put a switch here, and I can put a switch coming in the front door, all to turn on this light that's going to be on the ceiling fan here. All of these are going to go to that light. And that, two of them have to be three ways, and one of them has to be a four-way. But we don't label it like that on a plan. We label them all four ways, and then the electrician decides which one's going to be four and which two are going to be three.
Gotcha. Cost effectiveness.
Yeah. Yeah, because we don't, you know, we're not the specialist. We can only say this is what the customer wants. He wants, you know, he or she wants three light switches to this light. And it's the electrical contractor's knowledge of the code to know which one to do right, per se.
Awesome.
Okay, so the final is open. And so you guys have at it. You got all the chances in the world, okay? And it will close on Friday at 11:59, okay? 1 minute before midnight. So you have all the chances in the world, and you got 3 days to do it. Don't wait till Friday at 11 o'clock or Friday 11:50 to do it, okay? Take advantage of all of these chances that you have and get them done, okay? So if you have any questions during it, all you got to do is text me. All right. Remember that the test is as much of a learning experience as it is a testing your knowledge experience. So, you know, use it, utilize it, abuse it. Text me whatever you need to. I'm not going to tell you the answer, but I could probably tell you where to find it. Okay. I hope you guys have a very Merry Christmas if I don't talk to you again before then. So
yeah, thank you.
Have a great one, and hopefully I'll see you guys next semester.
Absolutely. Thank you so much.
Thank you.
All right.
Stay safe.
Yep, you too. You guys too. Have a good one. We'll see you.